Proving the irrationality of \sqrt $2. Theorem 1.3. Welcome, everyone. Before we dive into today's lesson, let's take a moment to reflect on what we have already covered. In our previous sections, we spent time learning the practical ways to identify irrational numbers, distinguishing them from the rational numbers we are more familiar with. We also explored a very important theorem regarding prime divisibility, which is a fundamental tool in number theory. Today, we are going to bring all of these ideas together. We aren't just going to identify numbers anymore. We are going to use those concepts to perform a formal mathematical proof, specifically to demonstrate that the square root of 2 is, in fact, an irrational number. Understanding the logic, an analogy. Now, before we dive into the algebraic heavy lifting, I want to pause and talk about the logic we are about to use. This method is called proof by contradiction, and it might sound intimidating, but it's actually quite intuitive. To help you visualize this, let's imagine a detective investigating a crime. Suppose there is a suspect who claims, "I was at home sleeping during the time the crime took place." This is their initial statement. However, while investigating, the detective finds a CCTV recording that clearly shows the suspect at the crime scene at that exact same time. Now, look at the conflict here. The fact that the suspect was caught on camera at the crime scene directly contradicts their claim of being at home. Because it is a logical impossibility for the suspect to be in two different places at once, the detective can conclude with absolute certainty that the original claim, that they were at home, must be false. In mathematics, we use this exact same strategy. Instead of trying to prove \sqrt $2 is irrational directly, we start by assuming the exact opposite of what we want to prove. We assume it is rational. Then, we follow the logical consequences of that assumption. If those consequences lead us to a logical impossibility, a contradiction, then we know our initial assumption was wrong, and therefore, our original goal must be true. Keep this detective mindset in mind as we move to the next slide to start the formal proof. Step-by-step proof. Now that we've understood the logic behind a proof by contradiction using our detective analogy, let's get down to business. On this slide, we define our clear objective for the mathematical journey ahead. We are going to formally prove that the square root of 2 is an irrational number. Step 1. The initial assumption. Now that we understand the detective analogy and how a contradiction works, let's move into the actual mathematical proof. To start our proof, we are going to use a technique called proof by contradiction. This means we aren't going to try and prove \sqrt $2 is irrational directly. Instead, we are going to begin by assuming the exact opposite of our objective. So, let us assume that the square root of 2 is actually a rational number. Now, if we assume it is rational, we must follow the formal definition of what a rational number actually is. By definition, any rational number can be written as a fraction. Specifically, the square root of 2 equals a over b. In this fraction, we have to be very specific about our terms. First, both a and b must be integers. Second, b cannot be equal to 0 because we know that division by 0 is undefined. And third, and this is the most important part for the logic of our proof, we must assume that a and b are coprime. When I say coprime, I mean that the fraction is in its simplest form, meaning that a and b share no common factors other than the number 1. You'll want to keep this detail in mind, because as we move into the next steps of the algebra, we are going to search for a common factor that breaks this rule, creating the contradiction we need to finish our proof. Step 2. Squaring and rearranging. Now that we have established our initial assumption in the previous step, we need to manipulate our equation to see what it reveals about the numbers $1 and $b. To get rid of that square root on the left side, we are going to square both sides of the equation. This gives us the square root of 2 squared equals the fraction a over b all squared. When we perform this operation, the square and the square root cancel each other out, which simplifies the left side to just the number 2. On the right side, we are left with a squared over b squared. To make this easier to work with and to prepare for our next step involving divisibility, we want to clear the fraction. So, we multiply both sides of the equation by b squared. This leaves us with 2 times b squared equals a squared. We will refer to this as equation 1, and we will be coming back to this specific expression very shortly to apply our theorem on divisibility. Step 3. Applying Theorem 1.2, divisibility of a dollar. Now, let's take a closer look at equation 1, which we derived in the previous step. Looking at the equation, 2b squared equals a squared, we can clearly see that a squared is equal to 2 times the integer b squared. Because a squared is a multiple of 2, this tells us quite simply that 2 divides a squared. Now, this is where we bring in a very important tool from our earlier lessons, Theorem 1.2. As a reminder, this theorem states that if a prime number p divides a squared, then that prime number p must also divide a in our specific case. Since 2 is a prime number, and we have just established that 2 divides a squared, the logic dictates that it must also be true that 2 divides a. Keep this result in mind, because we are going to use it in the next step to perform a substitution. Step 4. Substitution and divisibility of b dollar. Now that we have established in the previous step that 2 divides a, we need to use this information to see what it tells us about b. Since we know that a is divisible by 2, we can mathematically express a as 2 times some other integer. Let's call it c. So we write a equals 2c. Now let's take this new expression for a and substitute it back into our first equation, which was 2b squared equals a squared. When we replace a with 2c, the equation becomes 2b squared equals the quantity 2c, all squared. If we expand that square, we get 2b squared equals 4c squared. To simplify this, we can divide both sides of the equation by 2, which leaves us with b squared equals 2c squared. Take a close look at this result. B squared is now equal to 2 times the integer c squared. This clearly shows that 2 divides b squared. And just like we did within the previous slide, we can apply Theorem 1.2 here. Since 2 is a prime number and it divides b squared, it must follow logically that 2 also divides b. We are now halfway to our contradiction. Step 5. Identifying the contradiction. Now, let's bring everything together to see the aha moment of this proof. Let us look closely at our findings from Step 3 and Step 4. From our work in Step 3, we established that 2 divides a. And from our work in Step 4, we discovered that 2 also divides b. If both a and b are divisible by 2, this means that a and b share at least one common factor, which is 2. But remember back in Step 1, when we first set up our initial assumption, we specifically stated that a and b are coprime, which means they have no common factors other than 1. Do you see the problem? We have reached a contradiction. We have 2 statements that simply cannot both be true at the same time. This brings us to our final conclusion in the next slide. Final conclusion. Take a look at what we just discovered in the previous steps. We found that both a and b are divisible by 2, which directly clashes with our starting point where we stated that a and b were coprime. This contradiction, this logical breakdown, didn't happen by accident. It arose specifically because of our initial assumption that the square root of 2 is a rational number. In mathematics, when an assumption leads us to a logical impossibility, like finding a common factor where we explicitly said none existed, it serves as definitive proof that the original assumption must be false. Therefore, since we have proven that the assumption of rationality is impossible, we are left with only one logical conclusion. We conclude that the square root of 2 is, in fact, irrational. We have successfully completed our proof. Now that we have reached this point, let's bring everything together for our final conclusion. Key takeaways. First, let's look at the method we used, proof by contradiction. As we discussed in our detective analogy earlier, this is a powerful logical tool. Instead of attacking the problem directly, we start by assuming the exact opposite of what we want to prove. We then follow the logical consequences of that assumption until we hit a dead end, a logical impossibility. When that impossibility appears, it proves that our starting assumption must have been wrong. Second, I want to emphasize the importance of the Copper-Mirror requirement. You might have wondered why we specifically stated that A and B have no common factors. This is the most critical part of the setup. Without the requirement that A and B are coprime, finding out that they are both divisible by 2 wouldn't be a problem. It wouldn't be a contradiction. The contradiction only exists because we previously claimed they had no common factors. Finally, let's reflect on the role of Theorem 1.2. This theorem was the engine that drove our proof forward. It provided the mathematical bridge that allowed us to move from the divisibility of a squared to the divisibility of A itself. Without this specific property of prime numbers, we wouldn't have been able to conclude that A was even, and the whole proof would have stalled. Now that we have successfully completed the proof, let's take a moment to recap the key takeaways from today's lesson so you can solidify your understanding. Keep these 3 pillars in mind, as they are fundamental to understanding not just this proof, but many proofs you will encounter in higher-level mathematics. Common mistakes to avoid. First, let's talk about forgetting the coprime condition. This is perhaps the most critical part of our setup back in step 1. When we assumed that square root of 2 equals A over B, we explicitly stated that A and B are coprime. If you forget to mention that they have no common factors, then when we later discover that 2 divides both A and B, you haven't actually found a contradiction, you've just found a common factor. A contradiction only exists if you have previously claimed that no such common factors exist, so never skip that definition. Second, be careful about skipping the substitution step. In step 4, you saw how we took the fact that 2 divides A and expressed it as A equals 2C. Some students try to jump straight from saying 2 divides A to saying 2 divides B while the logic is correct. In a formal mathematical proof, you cannot take leaps of faith. Every logical step must be supported by algebraic work, specifically by showing that substitution back into the equation leads to the result. Finally, make sure you don't confuse the definitions of rational and irrational numbers. Always be precise. When defining a rational number, you must clearly state that it can be expressed as a fraction, A over B, where A and B are integers and B is not equal to 0. Being precise with your definitions is the foundation of all mathematical proofs. Now, as we wrap up this lesson, I want to touch on some common pitfalls. Even when you understand the logic of the proof, there are specific areas where students often lose marks in exams. That concludes our session on the irrationality of the square root of 2. Keep practicing these formal structures, and I will see you in the next lesson.